Thank you for attending today's meetup. And welcome to the webinar on 5 key elements of infrared camera OEM integrations. My name is Scott Bosberg, part of the marketing team here at Sierra-Olympia Technologies. Today's presentation is one of many webinars from the UAV Manufacturers Meetup Networking Series by Micropilot. Today is a rescheduled event that was originally supposed to air on June 27th, but was rescheduled due to COVID reasons. If you're interested in participating in other webinars, you can bookmark the link that I'm going to drop in the chat. And there is the most updated schedule of future webinars. We intend for this presentation to be interactive, so please use the chat window to send questions for the presenters. At the end of the session, we will have time to answer some questions and can unmute attendees to ask questions directly. If you think of a question after the presentation, or we ran out of time to answer your question, please email us at marketing@sierraolympic.com, and we will make sure Tim or Andy has the chance to respond to you. We are recording today's webinar, and that recording will be posted on our website around before July 22nd. So today's speaker, Tim Decker. Tim has graduated with a Bachelor of Science in Mechanical Engineering and a math minor from the University of Iowa. He has worked in the Columbia River Gorge UAV-based tech industry and around Hood River, Oregon for 11 years. His experience spans test development of the in situ RQ-21 UAV cloud cap ISR gimbals and extends to wakeboard manufacturing for slingshot sports. Over his 5 years with Sierra-Olympia, his knowledge and expertise has informed end-to-end system architecture for a variety of products, customer programs. As product engineer manager at Sierra-Olympia, he is a liaison between the engineering team and customer success. Andy Crafts holds a Bachelor of Science in Computer Engineering from Cal Poly San Luis Obispo. He has worked for more than 10 years in the drone industry, serving as an electrical engineer, computer software engineer, and wearer of many technical hats at a variety of small companies. He recently joined Sierra-Olympia as a systems engineer and has deep experience in working on infrared cameras, RPAS, and autopilot integrations. Andy is named as the inventor on US Patent 11391068B2, apparatus and method for automated launch, retrieval, and servicing of hovering aircraft. Our 5 topics today will cover product classes, interfacing, software requirements, video requirements, business relationships, and then at the end, we'll have a QA with the audience. Now I'd like to present to you a word from our president, Chris Johnston.
My name is Chris Johnston. I'm the president and founder of Sierra-Olympia. Broadly, Sierra-Olympia Technologies is an infrared camera innovation company. We've always been at the top of the technology pyramid throughout our 25 years in history, always dealing with the latest sensors available, always pushing the limits with optics and integration. And our mission is to continue to pursue that path, always leaping over the current technology and trying to get to the next technology level ahead of the market.
So during this presentation, I'll start talking about how our diverse portfolio of catalog items fulfills that mission. And as Scott said, we have the topics listed, interfacing, software requirements, and so forth. The general idea is what sort of things are important if I am considering integrating thermal technology. What sort of things do I want to consider? And particularly, how do Sierra-Olympia products make that easier? So I'll start talking about Sierra-Olympic products. In this presentation, we'll cover two main classes of them, mid-wave and long-wave infrared, thermal infrared. Those two classes refer to different spectra that the cameras can see of thermal energy. Each of those has its own advantages and disadvantages. I won't get too deep into the technology and why they see certain parts of the spectra, or what part of the electromagnetic spectrum is relevant to one application or another, but I can talk about the products that we create and the differences between them. So we have some in front of us right here. We have a mid-wave camera called a Ventus 700, a Tenem long-wave camera, and a Vinden long-wave camera that's been integrated into a tube. So I'll refer to these throughout. And so this is a mid-wave camera. This is a big guy. It's called the Ventus 700. Generally, mid-wave cameras have a few characteristics. They're higher size, heavier, and they have a higher power draw. And one of the reasons is that they have a cryo cooler. So they have a liquid nitrogen cooler that cools down the focal plane, which makes them more sensitive. It's necessary for the material technology that's in the focal planes. So that cryo cooler makes them more sensitive, but also makes for a higher cost of ownership. So it makes them heavier, more power draw, and a higher cost of ownership. That can be upfront costs, that can be maintenance costs, so forth throughout the lifetime of the camera. But what you get for that is dollar for dollar a better performing long range camera. So this camera has an incredibly long focal length. It can see great distances. And where long wave cameras might suffer from attenuation from the atmosphere, on a mid-wave camera, it is sensitive enough to cut right through that. And the absorption band is right. That goes back to it being mid-wave versus long wave. So I also have two long wave cameras, and you can see this is a Tenem. This is a 10 micron microbolometer core, and obviously it's much smaller. It also doesn't have quite the same magnification as this guy. But in general, long wave cameras are smaller, lighter. They have lower power draw, lighter optics, but they're required to use less sensitive optics. So the optics can be smaller and cheaper and lighter weight, because the focal plane technology is a completely different technology. So where mid-wave cameras use photovoltaic detectors that are like a CMOS or CCD camera, long-wave cameras use microbolometers, which is a different type of technology altogether. And because I won't go into great detail in this webinar about those technologies. If we have questions, I hope that anyone poses them, and I'd be happy to talk about it more in detail. But just knowing that they use different sorts of sensor technologies, and they each have their own advantages and disadvantages. So Sierra-Olympic also has different other types of product classes. So we do different lens integrations. This is a zoom lens. This is a fixed lens. And then in this enclosure is also a zoom lens. So we do mostly zoom and fixed lenses. And in thermal technology, we'll talk about this more later. Thermal technology, zoom is harder than visible cameras. So it's quite easy to buy something like a Sony Blot camera. You have a zoom button and it just works. But it's a bit more tricky with thermal cameras. We'll talk about why that is later. And then the other value that Sierra-Olympic provides is putting different interface options on this camera. And that's what we'll spend a great deal of time talking about in this presentation. So we have a variety of types of kind of back ends for these sensors that we talk about, and then a variety of different types of integration methods. So this is kind of a fuller integration. This is a ready-made enclosure, and it's aluminum, and it's powder coated, and it's weather resistant, and it's designed for long-term installation in terrestrial applications. So we run the whole gamut, and we do kind of different combinations of these technologies, right? The different sensor technologies, the different levels of integration, different optical technologies. So some of those are highlighted here. Some of the more unique ones, especially on this page, we have HD, so 2 megapixel long wave cameras. The Vayu HD is the only 1920 by 1200 long wave camera available commercially. We have the Ventus OGI, which is a mid-wave optical gas imager. And so that has special filtering technology that allows it to see methane. which is very, very useful in oil and gas applications. And we have some enclosed and distributed cameras that are highlighted on all. These, of course, are available on our website in great detail, and there are a lot more things on the website. And they're all built to be cameras as components. So what does that mean? In all of these cases, we have integrated some element of sensor technology, lens technology, control technology, software, and so forth. And we build them all into one component, and we allow that to be essentially dropped into a larger system. That's the general idea of how we create products. Is we take these technologies, put them together, and make them more convenient and easier to use and to integrate into a larger system. You don't have to figure out how to combine all these. You could certainly purchase these technologies separately, but figuring out how to combine them and how to make them work well together is the hard part that we try to solve for you in advance. Additionally, a lot of these components can be just difficult to get. So Sierra-Olympia is poised. We have a whole ecology of vendors and technology that we have access to, and we can recommend different technologies and recommend different products for different applications, and we can support customers and how to integrate those. And so Andy will talk about some of the technical details about system integration.
Hey there, Andy Crafts here. I'm going to go into more details on interfacing. As Tim mentioned, these are products that we combine into one component for you. So on the left-hand side of this page, you'll see a raw sensor and a timing diagram. On the right-hand side, you'll see a Sierra-Olympia offering, which is in a complete assembly that supports, that can go into your product as a complete system. And if you were to do this on your own, you need a mechanical engineer, somebody to design you an enclosure. You need a software engineer to process the signals, perhaps a firmware or electrical engineer to make boards to interface them. And instead, you can work with us and we will offer you ICDs. So we have, for all of our products, we have a complete technical package that has mechanical ICDs, electrical ICDs, and software ICDs. And I have examples, little snippets of those on this page to show you what that means for you. So we give you pole locations, CG location, mass locations. Then we also provide a software interface to control the camera or components within the camera. And we go into detail about the electrical interfaces and power requirements. So rather than having to sort through this yourself and stack up power requirements and look at inrush currents and figure out what you need to support that, we do all that for you and make it much easier for you to get this into your system as a component. Some of the other things that we offer that are kind of unique, like on this one, we have ingress protection. It's not IP rated, but we have done some testing with the hose and thermal ranges and then for cooling. So a lot of these components create heat and you want to keep the focal plane somewhat regulated. So we sometimes have heaters or coolers or fans inside of the assemblies to keep everything copacetic. One of the other nice things about working with us is that we make our interfaces standard. So our connectors are standardized, our voltages are standardized, and the way that you communicate with our products in terms of how the ones and zeros go through and what the video interfaces are somewhat standard across our product line. There's variation across them. You know, you're not going to have the same output on a UVC camera as you would as an Ethernet one, but once you get into our ecosystem, you can kind of try different things within our product line and see what works for you. So all of this, the goal of this is to lead to a shorter integration time for you. You can remain an aerospace expert or a search and rescue expert, and you don't have to get into the how and the why of thermal cameras. You can just use it as a tool within your product line. So we can remain focused on thermal cameras and everything that that goes behind that, and you can remain focused on your goal, your company's goal. So next I'll go into a little bit more detail on the software interfaces and electrical interfaces. They kind of play together. So we have two primary interfaces that we offer to customers. There's other ones as well, like HDMI, camera link, Gigi, SDI, and MIPI. But the two big classes that we like to work with are encoded video and raw video over UVC. So UVC is plug and play. Most webcams are UVC compatible. You get full bit depth video from it. And it might look something like this image on the left-hand side, completely raw out of the sensor. A lot of our UVC devices do offer some image enhancement. So you could have clawheat and or false coloring. You might be able to get something like these further to the right images out of that UVC device. But onboard processing is somewhat limited. Typically, that will be plugged into another computer, whether it be a laptop or a NVIDIA Jetson GPU, something of that sort. Then you might be doing some higher level processing on that. The other option that we commonly work with is encoded video. So we have H.264, H.265 encoded video, and that encoder offers a lot more features as well. So we can, if you're integrating onto gimbal, it can offer object tracking. It can inject KLV metadata, which on drone applications can be super helpful. And then it can also do higher level clawheat and other image processing functions. That allows you to compress the video and then downlink it over an Ethernet radio. So again, for drone applications, that can be super helpful. You don't need to feed it into another system to do that encoding. We can provide you a 3 megabit video stream rather than the UVC device might be hundreds of megabits. One thing Tim mentioned earlier about the difficulty of zoom as well on thermal cameras, this encoder can provide some non-uniformity correction to lenses across the zoom range. So we'll have at different zoom indexes, different non-uniformity tables, and can correct across the whole zoom range rather than at one focal length. The software that runs on our encoder standardizes the lens control, and it handles all the camera initialization and power sources. And it also can communicate with other devices in your system. We've done laser rangefinders, GPS units, and a lot of our MWIR assemblies have a shutter as well, and we handle the control of the shutter. I previously mentioned our ICDs, and we obviously have an ICD for our software, and then we also provide a GUI that interacts with that ICD so that out of the box you can start twiddling some of these knobs and playing with the different settings and seeing how it works, and then in the end develop your own software interface if appropriate. The final thing I'll say on this is that the software itself doesn't take up space, but the hardware that they run on does. And our electronics can be very small, or they can be slightly bigger or bigger yet. And it can have an impact on size, weight, power, and cost. And those, for drone applications, those can be really important. So our encoded product line might be a little bit more costly, might use a little bit more power, but you can get them quite small and low weight. And the video is encoded. You don't need to add a secondary computer to do the encoding for you. And it can plug into your system and be ready to go. Next up, we will bring Tim in to go into more detail about thermal video.
Thank you, Andy. So we've talked about a lot of the techniques, a lot of the things that go into making a good infrared camera system and how you marry all these components together. And at the end of the day, the goal is to gather information, right? Gather visual information. At the end of the day, a thermal camera is a camera. And so what you want to get out of that camera is good video. And what is good video? So good video starts with good requirements and some analysis and some tuning and some measurement. And these are all things that we do at Sierra-Olympic when we design and build camera systems. So often there's like a pre-sales phase when we work with customers or when we are designing a system that is meant for a certain project or a certain customer. And in this pre-sales phase, we like to consider a lot of different things that affect the performance of a thermal camera system. So spatial sampling, or how much zoom there is, like in visible cameras, this is often expressed as like 20x zoom or in focal lengths. And it's essentially how much are you magnifying each pixel. So two sensitivity metrics often used in thermal camera technology are resolvable temperature difference and NETD. And it's very important to consider these, very important to try and optimize these parameters, because thermal cameras have a generally higher noise floor, generally noisier, generally have different sensitivity than most visible cameras. So in general, kind of one theme that I'll come back to is that visible cameras tend to be easy, right? It's very easy to buy Imperx or Sony block cameras and Sony kind of previous modules that are made by a variety of types of vendors. You can get off the shelf optics and you can screw them in and know that it'll work quite well. And you'll have to do minimal work to get those tuned together well. Thermal cameras are a little bit more of an unwieldy beast. So I'm going to continue going down this list of things that generally have to be considered when you integrate that technology and want to get the most performance possible. So these are things that we consider while we're designing, before we're designing, and during build. So moving on, detectability distance ranges. So this is often called DRI. You'll see that written in the specifications as DRI often, which is detection, recognition, and identifiability. So that takes magnification. Like, for example, if I have an object 100 meters away and it's a wrench and I want to render 4 pixels across this 12-inch wrench, I know that I have to magnify that area enough. But I also know that for a thermal camera, there has to be a certain amount of humidity in the air, or the temperature difference has to be great enough. So the DRI modeling takes into account the atmosphere and the conditions of the objects that you're measuring. And we have the ability to do simulation and modeling that can predict DRI ranges for different types of cameras. MTF optimization. So the worst thing that you can do on a multiple $10,000 mid-wave camera system is put a bad lens in front of it. And that's something that we see happen often in cheaper integrations or rushed integrations. And one of the key tenets that we have here at Sierra-Olympic is that you don't destroy good sensors with bad optics. So one way to do that is we can do MTF modeling and measurement and ensure that we are as close as possible to diffraction limited performance for a given sensor platform. And so we will beforehand try to model what we expect, how sharp we expect a lens should be in a certain platform. And as we integrate it, as we align the sensor with the lens and fix all the components together, we will afterwards measure that MTF to make sure that we have gotten the most amount of performance out of that optical terrain as possible. And then with zoom lenses like this, bore sight is important. So bore sight is co-alignment of a camera system to some other reference. And often that is, maybe you have a infrared camera and a visible camera, and you want to make sure they're pointing at the same thing. That could be any peripheral, though. It could be some reference surface on a device. So for example, in a robotic application, you might have a ground vehicle, and you say that the ground itself is your reference surface. So I always want to know where my thermal camera is oriented relative to the ground and relative to the forward travel of that vehicle. And so being able to build in alignment features and mounting features into a camera that promotes consistent, repeatable, and easy alignment to some other orientation is very useful. And then being able to characterize, especially for a zoom lens, how that might wander over the zoom range. So as you zoom in, you might find that the center pixel drifts. And that's just kind of a natural characteristic of larger zoom lenses. And we have the ability to measure that, and in some cases correct for that. And so we have some graphs shown on this slide that show some of these measurement techniques. And these are all things that we can produce on a unit basis generally and report them and correct them if any of them are out of specification. So aside from these kind of performance limits, there are also things that we consider for a given integration that are a little bit more touch and feel. And so you want to make sure, in addition to kind of wringing out all of the performance you can from a given integration, you want to make sure that it's going to work well in your system. So we concentrate on the digital workflow. So as we produce that information from the camera, how do we maintain its fidelity? How do we use that and employ it in the most efficient way possible? And then is there anything that we can do with that data to process it and get even more information out of a given frame of data? So I have an example here of a block diagram that a customer might use when integrating some of our products. And of course, this is an example. There are 100 ways that you can integrate any given camera. But this is something the sort of thing that we've seen before often. So how do you use good thermal video once you've created it? In this block diagram, we have a Sierra-Olympic camera with the video encoder, or I've called it the image processor here, the video encoder that Andy was talking about earlier. And we generally use video encoders from a partner company called Sightline. They're co-located here in Hood River. And if you're on this webinar series, you've probably heard from them before. They make fantastic products, and we utilize them across our whole product line, and they're very functional. And so this diagram illustrates a way that you can utilize all of the functionality of such an encoder in our camera. So Andy had mentioned that there are multiple types of outputs, and they're simultaneous. So in this block diagram, I have written that a few different pipes for this data. So we're taking raw data, raw video, and piping it into some sort of analytical processor. So Andy mentioned NVIDIA Jetson or some other kind of compute device. It might be running a machine learning model or a classification model, and it might be looking at that raw video and using the full bit depth, so the maximum amount of fidelity possible, and running a classification model to say, oh, there's a car in the frame in the top left. And so it might reduce that down to some sort of metadata that can then be fed back into the image processor, the Sightline encoder. And alongside that, you might have some other peripheral GNSS device or a rangefinder that might be generating its own metadata that also gets piped into that image processor. And so then these things get coordinated with the video. And so for a given frame of video, it might say, I'm at this location and I can see a car in the frame, and the car is in this video location. And it packages that with the frame of data and then outputs that over Ethernet into the rest of the block diagram, right? So in some cases, that's probably some sort of edge device. It might be a video management system or a digital video recorder or a larger network architecture or even just a client computer, right? And then that might go somewhere else. That might go to a number of different clients or a storage device or a monitor. And we have different interfaces that make that easy to do. And there are a lot of ways, even from what you plug into the camera to the sort of networking software that lives on that camera. So it can essentially be a computer that is a video server. And again, there are a lot of different ways to skin the cat, a lot of different kind of morphologies of how you could put these things together. But they're designed to work in a lot of different situations. So chances are, if you have your own block diagram, that we have a way to integrate that together. So in addition to all of the technical aspects of integration and how you might design a system and put it together, it's also very important, of course, to develop a personal business relationship. And so our goal at Sierra-Olympic is to establish a relationship with our customers, and we like to do that over long-term projects, but we are happy to serve short-term projects as well. We like to bolster these long relationships or short relationships with a commitment to service. And we support that commitment to service in the following ways. So we're a small company here in Hood River, and we have, I mentioned a staff of about 15 engineers, and then in total about 30 people supporting the entire operation. And every one of these employees is works in customer service. So we enjoy working with customers, and it's very important to us. We find that that can be very important to their success. So everyone at the company is committed to customer service, and especially in the realm of technical support. One of the advantages of working with a small company like Sierra-Olympia is direct communication or collaboration with the engineering staff. So if we have technical issues, or you want to know how something works, or can I do this, can I do that? It's very easy to connect directly with the individual who might have designed that aspect of the camera, which is pretty unique and pretty neat. And I enjoy working with our great staff, and I hope that you will too. And we have, outside of engineering, we also have a lot of expertise in export compliance. So as you may know, that a lot of the technology is export controlled, or has some other sort of classification that can be hard to navigate. And we have dedicated staff that are expert in those areas and can assist in integration and assist a company working with the project and using this technology. And then for the longer term relationships, we have project management professionals that technical program management and project management. And we are excited and happy to work on a larger project with you that might need some project management expertise, and we can handle larger contracts and make sure that we coordinate with our customers to fulfill those. And finally, I'll talk a little bit about our facilities here that supports all of these goals. We have a 2,000 square foot class 10,000 clean room that we use for production and assembly. We have an 8,000 foot engineering area with lots of free space to roam and lots of area to do imaging and set up equipment. We have a full suite of environmental chambers that are used for unit testing and design development testing, collimators, black bodies, optical benches, all sorts of optical tools that we use to either play around with ideas or put together cameras and measure their performance. And to support design activities, we have a lot of rapid prototyping facilities. We have a machine shop and 3D printing, and of course, all sorts of design services. So if anybody has any questions about the working with Sierra-Olympic, I will open up, or any sort of questions about anything that we've covered in this presentation, or really anything at all.
We had one question earlier from somebody about working in the desert and what kind of considerations you might have for desert conditions and what unique things you might have to handle there.
Right. So in terms of optical performance, the question, I'll repeat the question literally, is it was mentioned that humidity was needed in order for the DRI system to work well. Do these cameras still work in extreme desert conditions? So there's kind of two parts to that. Is does the camera still work in, say, a hot and dry environment, or maybe an environment where there's a lot of dust? And it depends on how you integrate that, right? So this is an example of an integration. This is a long wave camera, and the guts of this enclosure look kind of like this. And so we can put this in a tube, and we can enclose that tube and seal it up. And so that will help a thermal dissipation from the hot desert sun in the hot environment. It'll help with ingress protection to make sure we don't get dust inside. And it will generally protect the camera from the elements. So in terms of can it survive the environment, that's one way that we can do that. And then does the camera work in a desert environment? So does it have good performance? And that depends on the sort of component selections that you make as well as the environment. So actually a desert is probably one of the best conditions to operate a thermal camera in, because it's hot and it's dry. And one of the issues with moisture in the air is that it attenuates signal in the thermal infrared portion of the electromagnetic spectrum. So you can't see through water, and you can't see very well through water in the air. The cameras generally work quite well in terms of performance in desert conditions.
Cool. That's the only question we've gotten so far. If anybody else has anything, you can enter it into the chat window now. I also just put in the URL for the schedule for the next set of meetings. And if nobody else has any questions, I think we'll wrap things up here shortly.
And if you do generate questions later, of course, we've always like to talk to our customers. So feel free to visit our website. You can find a potpourri of email addresses on there and lines of contact. You can get a hold of either of us or Scott or really anyone on staff. So if you think of questions later, please feel free to. This will be posted online, I think in a few days. It'll be available on our website, so this whole webinar. So if you want to go home and study and watch the presentation again and then ask some questions, we'd love to answer them. So another question that just came in, what kind of consideration for a congested area as well? Pierre Piolo, you might, if you could type in what you mean by congested. And without an answer, I'll maybe speculate on what how to use a thermal camera in a congested environment. So I can think of a couple different ways that might be congested. Maybe there's a lot of
Industrial site.
not in open areas such as an industrial site, right? So a lot of that comes down to selecting the right sort of making the right optical selections. So field of view, in other words, how wide or narrow, how zoomed in is the camera. One area that we have experienced doing large scale industrial integrations is oil and gas refineries. So if you can imagine that that's a very large area, it has a perimeter, and within that perimeter, there's a lot of equipment, there's a lot of stuff going on. There might be people and trucks moving in and out, there's towers and things that occlude views. So what a lot of our customers will do is say, in this perimeter, I'd like to have maybe 3 or 4 towers, maybe 4 towers at the corners. And I know that each of these towers already have surveillance equipment, already have cameras on them, and we need to be able to see at night. So we want to use thermal technology. How can I be sure that I can get away with 4 cameras in these corners and still be able to see anything? Or do I need more, or do I need less? And so we can do modeling that considers the field of view of a given camera. In other words, how zoomed in is it? And how many pixels are rendered over that field of view. So I know that if I have a very low resolution camera and it's looking in a wide area, I don't have a lot of pixels that span that wide area. And so anything that occludes that frame, I won't really have enough resolution to see through or see around. So if I'm looking through a fence or I'm looking through a piping lattice or something like that, you're going to want a lot of resolution to be able to see through those things. And then generally making sure you have enough coverage in those corners, making sure that the field of view is right so that you can see the whole expanse. And so we can do modeling in advance to simulate some of those conditions.
One thing I'll add is something like this, where you have an adjustable zoom lens, can be really helpful, because then you can have a wide area for monitoring. And then if you see something of interest, then you can zoom in on that particular area. And then also this product here is kind of meant for that application. We have mounting holes on the bottom, so you can put it on a pan tilt unit. And that's what it was kind of designed for, is to go onto a pan tilt unit and on an industrial location and look around.
So in terms of the presentation is called the 5 key elements of integrating thermal technology. It's not only thermal technology. It's of course within the camera, having a zoom lens is good, but also, if your goal is to images in a congested area, and you might not know that, wow, there are cameras available that easily sit on a pan tilt unit, and boy, I'm just learning what a pan tilt unit is. These are things that we know off the back of our palms. So one of the key elements to thermal integration is system design and making sure you generally have the right equipment across your system. And we can certainly offer some expertise in that area. And with that, looks like the chat window has calmed down. So once again, we'll close out. This presentation will be available online, and any of the Sierra-Olympic staff will be available through contact lines on our website. And if you have any more questions or want to know more about our products, you can please reach out. Thank you for joining.